So let us continue our study of partial fraction expansions. In the last lecture we have seen that in some forms there can be linear factors, in some forms there can be repeated linear factors, and some forms there can be quadratic factors and then repeated quadratic factors and so on. So in the last lecture we have seen how to handle linear factors. When you have distinct linear factors, then the Heaviside's cover-up method does the job for us, and you can explicitly compute what is the inverse Laplace transform for those functions. Now we will see in today's lectures repeated linear factors and quadratic factors. So let us begin with repeated linear factors. Repeated linear factors. So remember that these functions were rational functions of the form Ps over Qs, where of course Ps, Qs are polynomials, Qs we do not assume to be constant, non-constant, and you have degree of P is less than degree of Q, and here Qs is of the form s minus alpha 1 to the power m1 times s minus alpha 2 to the power m2, s minus alpha k to the power mk, and then you have s minus beta 1, s minus beta 2, and s minus beta L. So you have each of these is a repeated linear factor. So these are repeated linear factors because if mk is greater than 1, these are repeated linear factors, and these for these betas, these are linear factors. So we will first look at the case when you have just one repeated linear factor in Qs and the rest are linear factors. So let's start with an example. Fs is equal to s plus 1 over s squared times s minus 1 defined for s greater than 1. So here our repeated linear factor is this one, repeated linear factor, and this is our linear factor. So let me write the numerator as Ps and the denominator as Qs. So Ps over Qs can be written by as a partial fraction expansion. So for each repeated linear factor you have an expression of the form a1 plus s plus a2 plus s squared. So you have to continue until the highest power of s appearing in the repeated linear factor in the denominator. So you can also have here, for example, s minus some constant alpha, and here then will be s minus alpha, and then so if I take alpha, s minus alpha squared, then here it will be s minus alpha and here it will be s minus alpha squared. So for each repeated linear factor of power, let's say 2, then you have two terms, one with the first power, one with the second power, but in the numerator both are constants, there is no s in the numerators. And then you have the linear factor, which is b over s minus 1. So here so here of course the left hand side is s minus 1, this is our Fs, and so I will multiply throughout by by s square times s minus 1. So this is just qs. So then you will get s square times s minus 1 times s plus 1 is equal to, so a1 over s times s square times s minus 1. So one of the s's cancel out, so it's just a1 times s minus 1. Then you have a2 times simply s minus 1 because the s square terms cancel out, and then you have b times s squared. Okay. So on the left hand side we have s plus 1 simply because qs is our denominator here, and on the right hand side we have a1 times, so one of the s's will cancel out. Here we have an s square and here we have a s in the denominator, so one of the s cancels out and you get s times s minus 1 multiplied by a1, and on the second factor you will simply get s minus 1 because we have s square and s square in the denominator and numerator, and the third term will be b times s squared. So now you can compare coefficients of orders of s. So there are now two ways to do this. So first method to do this, to find a1, a2 and b, is to compare coefficients of s to the power k on both sides. So suppose we compare coefficients for s squared on both sides, so then you get 0 because there is no s square term in the left side, and on the right hand side you have a1 plus b, and then if you compare the coefficient of s, you get 1 on the left hand side, and on the right hand side you will have minus a1 plus a2. And thirdly, if you compare the coefficient of s to the power 0, which is the constant term, you will get on the left hand side 1, and on the right hand side you will get minus a2 simply. So here immediately you get the answer for a2, which is a2 is minus 1, and then you can solve for the other equations. So here you have a1 is simply a2 minus 1, so this is minus 2, and b is simply minus a1, so this is simply 2. So in this case we have 3 equations in 3 unknowns, and we can solve for these 3 unknowns to find out our coefficients for the partial fraction expansion. The second method is to plug in various values of s on both sides. So here we have, let's plug in s equal to 0, then we get, so this term vanishes, this term also vanishes, and on the left hand side you get 1, and on the right hand side you get minus a2. So again you get a2 equals minus 1 immediately. If you put s equal to 1, let's say, then the first 2 terms on the right hand side vanish because we have an s minus 1 factor, and so you get, on the left hand side you get 2, and on the right hand side you get b, which implies b equal to 2. This is what we got earlier as well, but in this case we cannot directly substitute any value of s to find out the value of a1. So Now we have to use the values of A2 and B to find the value of A1. So if we plug in, let's plug in S equal to 2 for example, or let's say I plug in S equal to -1, then on the right hand side you get a 0, and on the left hand side you get a 0, and on the right hand side the first term becomes -2 times A1, the second term is -2 times A2, and the third term is simply B. So this means that 2A1 is equal to B minus 2A2, and here we know already that B is 2 and A2 is -1, so this is +2, so you get 4 on the right hand side. So this implies that A1 is 2. So you get so one gets 2A1 equals, on the right hand side one gets -1 times -2 times A1 plus -2 times A2 plus B. So in the other hand we have 0 equal to 2A1 minus 2A2 plus B, which implies that 2A1 equals 2A2 minus B, and we know the values of A2 and B, so this gives you -2 and then again -2, so this is -4, so you get A1 equal to -2. So here the situation is somewhat simpler than the first method, because you sometimes you get directly the values for many coefficients, and rather than solving a system of equations in a system of n equations in n unknowns, many of the coefficients can be found directly, but some coefficients will be still unknown, and then you have to find those out using some system of equations. So there exists a Heaviside formula for these repeated factors as well. So Heaviside's expansion formula for one repeated linear factor. So in this case we have Fs equals Ps over Qs, and Qs is of the form s minus alpha 1 to the power m1, and then you have the rest linear factors b n, say. So the first one is a repeated linear factor, and the rest are linear factors. So for this function Fs, you have the partial fraction expansion of Fs is given by Ps over Qs is equal to A1 over s minus alpha 1 plus A2 over s minus alpha 1 square plus A m1. Well, let me just write m because there are no other exponents. So am over s minus alpha 1 to the power m, and then you have this linear factors b1 by s minus beta 1 plus b2 by s minus beta 2 and so on, bn over s minus beta n, where So the the b coefficients are known. So bi equals the limit as s goes to beta I, s minus beta I times ps over qs, which is simply p of beta I over q prime of beta I. So this is for I equal to 1 to n. So the question is, what are these? A1, A2 and Am. So this we know from the earlier Heaviside formula, expansion formula. Now this Heaviside's expansion formula for repeated linear factor is given by limit as s goes to alpha 1 over k minus 1 factorial, the derivative, the kth derivative dsk of s minus alpha 1 to the power m times fs. So this is the formula for the coefficient aj appearing. So j equal to 1 to up to m appearing in this partial fraction expansion. It is also not very difficult to derive the Heaviside's expansion formula for more than one repeated linear factors, and the formulas will be very similar, except you will have more alpha i's for the repeated linear factors, and the formulas for the coefficient appearing in those will be the same as this one, except you have to replace a1 by alpha 1 by the corresponding constant appearing in the repeated linear factor. So now let's look at an example for a quadratic factor. So let's take an example. So let me take fs to be s square plus 1 over s times s square plus 2. So I can rewrite it as s by s square plus 2 plus 1 over s times s square plus 2. So the first term is simply the Laplace transform of cosine of root 2t. So we know that this is from our known Laplace transforms. So let's just do the partial fraction for the second one, which is 1 over s times s square plus 2. So you can have the partial fraction expansion as a over s plus bs plus c over s square plus 2, and now you can multiply throughout by s times s square plus 2. So you will get 1 on the left side and a times s square plus 2 plus bs plus c times s. So on the right hand side one gets a plus b times s squared plus b plus cs plus 2a. So now you can let s equal to 0. So then you will find that on the left hand side you just simply have 1, and on the right hand side you have 2a, which gives you a equals half. Now there is a simple trick that one can use, which is to divide throughout by the highest power of s and then let s go to infinity in this case. So let's divide by s square on both sides. So you get 1 over s square equals a plus b plus c over s plus 2a over s squared. And now let s tends to infinity, so on the left side you get a 0 and on the right side you only get a plus b, because both these terms go to 0 as s goes to infinity, which implies that a equals minus b, which implies that b equals minus half. So you can evaluate the two of the coefficients like this, and now you can simply plug in any value of s in this identity, and we know the value of a and b, so that we can find out the value of c. So now let me plug in s equals minus 1. So then you get 1 equals a plus b, and then you have minus 1 times c plus 2 times a, and we know that a plus b equals 0, and so we get c equals 2a minus 1, but a equals half, so this is 0. So therefore we get that fs is 1 by 2 times 1 over s plus minus 1 by 2 times s over s square plus 2, which we have from this formula. And now we can immediately compute the inverse Laplace transform of fs. So the first term, since you have 1 over s, so this is simply half, because 1 over s is the Laplace transform for the function 1, which is equal to 1 everywhere. So half into 1 minus half times, again you have the cosine of square root of t. So we find this part of the inverse Laplace transform, and then you can add it to this part to get the final answer as well. So this is our fs here, so this is, let me call it f1s, and so f1s plus cos of root t will give you the inverse Laplace transform of fs. Now let's take another example where fs is equal to 1 over s square plus 2, and here I will solve it not using the same method, but using the method of complex roots. So note that one can write this as s square times s plus square root 2i and s minus square root 2i. So then you have the partial fraction expansion is of the form a1 over s plus a2 over s square plus b1 over s plus root 2i plus b2 over s minus root 2i. So we can use the techniques that we have developed for linear factors to solve for these coefficients, except that here you will get some coefficients which may be complex, and then there will be some complex conjugate answers which will combine to get you real values. So let's see what happens here. So if you multiply throughout by this factor s square times s square plus 2, then you get 1 equals a1 times s times s square plus 2, and then you have a2 times s square plus 2, and then you have b1 s squared multiplied by s minus root 2i. So one of the factors here I am writing s square plus 2 is s plus root 2i multiplied by s minus root 2i. So one of the factors for b1, s plus root 2i cancels out and you are left with s minus root 2i. Similarly, for b2 you have s square and s plus root 2i. And so you can combine the coefficients of all powers of s. So for s cube we will have one from here, one from here and one from here. So you get a1 plus b1 plus b2 s cube. For s squared you have one factor here and then one factor with this one and then again one factor with this one. So you get a2 minus root 2i b1 plus root 2i b2, this is on s squared, and then you have linear factors in s which is just a1 2a1 times s, and then the complex then the constant coefficient is simply 2a2. And now you can similarly solve for a1, b1 and b2 and a2. So let's see from the constant coefficient you immediately get a2 is half, and because the coefficient for s is 0 on the left hand side you get a1 equals 0. And so now you have two equations in b1 and b2 which we can solve. So one equation is b1 plus b2 equals 0. This is the coefficient of s cube, and you have half plus root 2i b2 minus b1 equals 0. This is the coefficient of s squared. So now from the first one you immediately get b1 equals minus b2, and so plugging this in, here you get from the second equation you get half plus square root 2i times 2b2 equals 0, which means that b2 equals minus 1 by 4 times square root 2 times I. Now you can take I upstairs by multiplying and dividing by I. So you will get I squared equals minus 1, and this minus factor cancels out. So you get in the end 1 over 4 root 2I as b2. So b1 is minus 1 over 4 root 2I. So now you can plug this in for our formula for fs, and we can use the fact that these factors, even though you have complex coefficients here, these are the Laplace transforms of e to the power whatever complex number you have multiplied by t, which the proof works exactly in the same way as for real numbers. And here you have the Laplace transform of e to the power minus root 2i times t, and so you will get L inverse of fs is equal to, so the first one a1 is 0, so you don't get anything. A2 is half L inverse of 1 over s squared, so this is simply t, and then you have b1 which is minus 1 over 4 root 2 times I, and then you have L inverse of 1 over s plus root 2I, and then again you have plus 1 over 4 root 2I L inverse of 1 over s minus root 2i. So let me just check whether this is the same thing I took here. So b1 has s plus 2i, root 2i, and b2 has s minus root 2i. So this is what we have written here. So then you get half t minus 1 over 4 root 2i, I is upstairs, exponential minus root 2i times t, and then you have 1 over 4 root 2i exponential square root of 2i times t. But now these two are complex conjugates of themselves, and you can combine them to get a real number, real function here. So let's see, you get, so let's take 1 over 4 root 2 outside, outside, then you get e to the power root 2 I minus e to the power minus root 2 I, and we can use the function for sine t. The formula for sine t in terms of the complex exponential is e to the power it minus e to the power minus it over 2i, and so we can use this here. So this is sine of 2i sine of square root t, and so now this I and this I give you minus 1. So in the end, using this formula, you get half t plus or minus 2 by 4 root 2 times sine of root 2t, and so this is half minus 2 root 2 sine of root 2t. So this is an easy enough function to check directly that you get the right answer. So as an exercise, check that the Laplace transform, so let's call this ft, the Laplace transform of ft is fs. So just substitute the known Laplace transform for these functions and you should get fs. So we end our lecture here, and we end our study of partial fractions as well. In the next lecture we will see the convolution theorem and how to apply all these methods for computing the inverse Laplace transform for solving various kinds of ordinary differential equations.